Right now, at this very moment, something ancient is sailing through the darkness above us. A visitor from the deepest reaches of space, carrying secrets from before our sun was born. It's been traveling for millions of years just to pass by our small blue world, and recently it put on quite a show. As you settle in to listen to this story, know that somewhere out there, beyond the reach of our most powerful telescopes, this cosmic wanderer continues its eternal journey, indifferent to our wonder, yet somehow making us feel more connected to the vast universe we inhabit. Welcome to Sleep About Science. Tonight we're exploring the remarkable journey of Comet 3I/AT Lars, that celestial wanderer that recently graced our skies and captured headlines around the world. And if you drift off to sleep while listening, that's perfectly wonderful. In fact, there's something rather poetic about falling asleep while contemplating an object that's been journeying through the cosmic dark for longer than humans have existed. Your dreams might carry you along similar paths through the stars, and that would be entirely appropriate. Before we begin, please make yourself comfortable. Pull those blankets up, adjust your pillows just right, let your body sink into whatever surface is supporting you, and remember, this is educational content meant to soothe and fascinate in equal measure. There's no test at the end, no need to remember every detail. This is simply a gentle exploration of one of the universe's recent gifts to our curiosity. If you haven't subscribed yet, you might want to, so you never miss these gentle journeys into the wonders of our universe. And wherever you are in the world, whether it's deep night where you are, or perhaps you're listening during a quiet afternoon, or maybe you're somewhere in between, know that you're part of a global community of curious minds who find comfort in learning about our cosmos. Take a deep breath, let it out slowly, and as you do, consider that the oxygen you're breathing has been recycled through stars, through space, through countless forms of matter over billions of years. Some of it might have been part of a comet once, just like 3I/AT Lars. We're all connected through these cosmic cycles, these endless transformations of matter and energy that make up the story of our universe. Now, let's begin with something remarkable. The comet we call 3I/AT Lars isn't really called that at all. That's just the name we've given it. Like putting a label on something ineffably ancient. The 3I tells us it was the third interstellar object we've ever confirmed. Yes, interstellar, meaning it came from beyond our solar system entirely. Think about that for a moment. Out of all the countless objects we've observed in space, we've only confirmed 3 that definitely came from other star systems. It's like finding a message in a bottle on the beach, and realizing it came not just from another country but from another ocean entirely, one that's not even on our maps. And Atlas? That's the asteroid terrestrial impact blast alert system that first spotted it. But this comet has been what it is for far, far longer than we've had words to describe it. Before humans developed language, before life emerged from the oceans, before Earth itself formed, this chunk of ice and rock was already ancient, already traveling, already carrying its cargo of primordial chemistry through the darkness. Imagine, if you will, a dirty snowball the size of a small mountain, tumbling slowly through the absolute cold of interstellar space. That's what 3I/AT Lars essentially is, minus a chunk of frozen gases, rock and dust, that's been preserved in the deep freeze of space since before our solar system even existed. Scientists believe it formed around another star entirely, perhaps one that died billions of years ago, sending this frozen time capsule on an eternal journey through the darkness. But let's think about what that really means. When we say it formed around another star, we're talking about a completely different stellar environment, possibly with different proportions of elements, different temperatures, different dynamics. That star might have been larger than our sun, burning hotter and faster, or smaller, burning cooler and longer. It might have been part of a binary system dancing with a companion star. It might have had its own family of planets, its own asteroid belt, its own Kuiper belt full of comets, and somehow, through some cosmic disruption, might as perhaps a close encounter with another star, perhaps the death throes of its parent star, perhaps the gravitational bullying of a giant planet. 3I/AT Lars was ejected from that system and sent on a journey that would eventually bring it to us. The story of how we came to know about 3I/AT Lars is itself a testament to human curiosity and the quiet dedication of astronomers who spend their nights scanning the heavens. It was discovered in early 2024 by the AT Lars system, a network of telescopes in Hawaii and South Africa that continuously photograph the night sky, looking for objects that might pose a threat to Earth. These telescopes never sleep, never rest. Every clear night they're taking pictures, comparing them, looking for anything that moves against the static backdrop of stars. Think about the patience this requires. Night after night, the telescopes and their human operators search through thousands of images, most showing nothing unusual. It's like looking for a single grain of sand that's slightly different from all the others on an endless beach. But they persist because they know that somewhere out there, something interesting is waiting to be discovered. And occasionally, very occasionally, they find something extraordinary. When astronomers first spotted this faint smudge of light moving against the background stars, they noticed something unusual about its trajectory. Most comets in our solar system follow predictable elliptical orbits around the sun, like cosmic figure skaters repeating the same routine over and over. They come in from the outer solar system, swing around the sun and head back out, only to return again years, decades, or centuries later. It's a cosmic dance that's been going on for billions of years. But 3I/ET/Alars was different. Its path was hyperbolic minus a mathematical way of saying it was moving too fast to be bound by our sun's gravity. It was just passing through. To understand how remarkable this is, imagine you're watching cars on a circular racetrack. They go around and around, lap after lap, bound to the track by the banking and barriers. That's like our solar system's comets. Now imagine a car suddenly appears from outside the stadium, cuts across the track at tremendous speed, and disappears out the other side, never to return. That's 3I/ATLS. It wasn't part of our local racing circuit. It was on a cross-country journey that happened to intersect with our track for just a moment. This realization sent quiet ripples of excitement through the astronomical community. Interstellar objects are incredibly rare. Most, or at least our detection of them is. Before 2017, we had never confirmed seeing one. Think about that. For all of human history, from the first time our ancestors looked up at the night sky to the invention of the telescope to the space age, we had never knowingly observed an object from another star system. Then came Oumuamua, that strange, elongated visitor that sparked so much speculation. Its name, Hawaiian for scout or messenger from afar, arriving first, captured perfectly the sense of wonder and mystery it brought. After that, Comet Borisov in 2019, named after the amateur astronomer who discovered it, and now, 3I/ATLAS. 3 confirmed interstellar visitors in just 7 years, when for all of human history before 2017, we had seen none. It's as if we suddenly developed a new sense, a new way of seeing the universe that revealed things that had always been there but that we'd never noticed before. But here's something gently mind-bending to consider. As you settle deeper into your pillows, these objects aren't actually rare at all. Scientists estimate that there might be more interstellar objects passing through our solar system than there are solar system objects themselves. Let that sink in for a moment. Right now, as you listen to these words, there could be thousands, perhaps millions of these ancient travelers silently sailing through our cosmic neighborhood, too small or too dark for us to see. We're surrounded by a gentle rain of interstellar visitors, and we've only just developed the eyes to see a few of them. Some scientists have calculated that at any given moment, there might be at least one interstellar object passing through the volume of space within Earth's orbit around the Sun. They're like cosmic neutrinos, those ghostly particles that pass through Earth by the trillions every second without us noticing. The space between planets, which seems so empty to us, is actually crisscrossed with the paths of these wanderers, each one carrying stories from distant stars. The journey of 3I/ATLAS to reach us is almost incomprehensibly long. Based on its trajectory and speed, astronomers calculated that it had been traveling for at least several million years before arriving in our solar system. Some estimates suggest it could be much older, might perhaps billions of years old, formed in the early days of our galaxy when stars were younger and more violent, when planetary systems were still figuring out how to arrange themselves. To put this in perspective, let's trace backward through time. 1 million years ago, our ancestors were just learning to control fire. The ice ages were in full swing, with glaciers advancing and retreating across the continents. 10 million years ago, our ancestors were still essentially apes, living in trees in Africa. 100 million years ago, dinosaurs ruled the Earth, and flowering plants were just beginning to transform terrestrial ecosystems. 1 billion years ago, life on Earth was still microscopic, and the most complex organisms were simple colonies of cells. And all that time, 3I/ATLAS was traveling through space, patient and silent, carrying its load of ancient ice toward a rendezvous none could have predicted. When it began its journey, the stars in our night sky were in completely different positions. Some of the stars we see tonight hadn't even been born yet. Others that were shining then have since died, their light finally fading from the universe. The galaxy itself has rotated several times during 3I/ATLAS's journey, Our entire solar system has completed numerous orbits around the galactic center, while this comet traveled in what to it was essentially a straight line through space. Picture this comet's journey for a moment. For millions of years, it drifted through the profound emptiness between stars. Out there, in interstellar space, the darkness is absolute. There's no nearby sun to warm it, no planets to provide companionship. The temperature hovers just a few degrees above absolute zero, meaning as the coldest temperature possible, where even atoms barely move. In this environment, time almost seems to stop. Chemical reactions that would happen in seconds on Earth might take millions of years in the deep freeze of interstellar space. In that darkness, 3I/ATLS was more isolated than anything we can imagine. The nearest star might have been light years away, tens of trillions of miles. If you could somehow stand on its surface, the stars wouldn't look like points of light as they do from Earth. They would be mere pinpricks, hardly distinguishable from the cosmic background radiation. The Milky Way wouldn't be a band across the sky, but a faint, diffuse glow. It would be the loneliest place imaginable, a frozen raft drifting on an ocean of nothingness. For eons uncounted, 3I/ETLAs tumbled through this cosmic wilderness, rotating slowly, perhaps once every few hours or days. This rotation was likely imparted when it was first ejected from its home system, and in the absence of any forces to slow it down, it continued spinning at the same rate for millions of years. It's a perfect example of Newton's first law of motion: an object in motion stays in motion unless acted upon by an external force. And in interstellar space, there are essentially no external forces. During its journey, our entire world changed in ways that boggle the mind. When 3I/ATLS began its voyage, there were no humans on Earth. Depending on exactly how long it's been traveling, there might not have been any life on land at all. Continents drifted thousands of miles, crashing into each other to form mountain ranges, splitting apart to form new oceans. The Himalayas might not have existed when 3I/ATLS started its journey. The Atlantic Ocean might have been narrower, or perhaps it hadn't even formed yet. Species emerged and went extinct by the millions. Entire evolutionary lineages rose and fell. The first flowers bloomed and died. The first birds took flight. The first mammals scurried through the underbrush. And eventually, after countless generations of evolution, a species emerged that would develop the ability to look up at the sky and wonder about the points of light they saw there. And all the while, this small frozen wanderer continued its patient journey through the dark, unknowing and unknown, a messenger from another time and place, waiting for its moment to deliver its message. And then, something remarkable happened. As 3I/ATLS approached our solar system, it began to feel something it might not have experienced for millions of years: the gentle tug of gravity from our sun. Even from billions of miles away, our star's influence reached out like invisible fingers, ever so slightly bending the comet's path. At first, this deflection would have been almost imperceptible, a change of perhaps millimeters per year in a journey spanning light years. But as it drew closer, the sun's influence grew stronger. It's worth pausing here to appreciate the elegance of gravity. Every object with mass in the universe attracts every other object with mass. You're gravitationally attracted to the device you're listening to this on, to the walls around you, to the earth beneath you, to the moon, the sun, and yes, even to 3I/ATLS, wherever it is now. These forces are usually too small to notice, overwhelmed by Earth's much stronger pull. But in the emptiness of space, even the tiniest forces can have profound effects given enough time. The sun's gravity reached out across the void and found 3I/ATLS. Perhaps when it was still a light year or more away, that's about 6 trillion miles, a distance so vast that light itself takes a year to traverse it. But gravity is patient and persistent. Mile by mile, year by year, it pulled the comet toward our star. Not enough to capture it. Mighty Earth. 3I/ATLS was moving too fast for that, but enough to curve its path into that distinctive hyperbolic trajectory that would eventually give it away as an interstellar visitor. As 3I/ATLS fell toward the sun, lines and falling really is the right word. Even though there's no down in space, something beautiful began to happen. For the first time in perhaps millions of years, the comet began to warm up. The change was gradual at first. When it crossed the orbit of Neptune, 30 times farther from the sun than Earth, the temperature on its surface might have risen from near absolute zero to perhaps negative 370 degrees Fahrenheit. Not exactly balmy, but warm enough for some interesting chemistry to begin. The frozen gases that had been locked in solid form for millions of years began to sublimate. That's the scientific term for when a solid turns directly into a gas without becoming liquid first. It's what dry ice does at a Halloween party, but on a cosmic scale. Different molecules sublimate at different temperatures. First might have been carbon monoxide, one of the most volatile substances in comets, then carbon dioxide. As the comet drew closer to the sun, water ice began to sublimate too, creating jets of vapor that burst from the comet's surface like geysers. These jets are one of the most dramatic phenomena in our solar system. Imagine standing on the surface of 3I/ATLAS as it approached the sun, ignoring for a moment that you'd instantly freeze, suffocate, and be bombarded with radiation. You'd see the landscape around you beginning to change. Cracks would appear in the ice, strange fogs would rise from the surface, and then suddenly a geyser of gas and dust would erupt nearby, possibly shooting material miles into space. These jets can be powerful enough to actually change the comet's rotation or even its trajectory slightly. This sublimation created what we call a coma, not the medical kind, but a glowing cloud of gas and dust surrounding the comet's nucleus. The word comes from the Greek for hair, because early astronomers thought comets looked like hairy stars. This description is more apt than they might have realized. Just as hair streams behind someone running in the wind, the coma streams away from the comet's nucleus, pushed by the pressure of sunlight and the solar wind. As you drift towards sleep, you might appreciate knowing that when ancient peoples looked up at comets, they often saw them as cosmic messengers, harbingers of change, or visitors from the realm of the gods. The ancient Chinese called them broom stars, imagining them sweeping across the heavens. The ancient Greeks saw them as stars with flowing hair. Some Native American tribes saw them as traveling spirits. In a way, they weren't wrong. 3I/ATLAS really was a messenger from another realm, another star system entirely. And it did herald change, at least in our understanding of how common interstellar visitors might be. Throughout history, comets have inspired both wonder and fear. They've been blamed for plagues, wars, and the falls of empires. They've also been credited with bringing good fortune, marking the births of kings and heralding new ages. The Great Comet of 1577 helped convince Tycho Brahe that the heavens were not immutable, setting the stage for the scientific revolution. Halley's Comet, which returns every 76 years, has been recorded by human observers for over 2,000 years, a thread connecting civilizations across millennia. 3I/Atlas joined this grand tradition, but with a twist. Unlike Halley's Comet, which is a familiar visitor, a cosmic neighbor that drops by every few generations, 3I/Atlas was a complete stranger. It had never been seen before, and would never be seen again. It was like the difference between a neighbor who visits regularly and a traveler from a distant land who passes through your town once on their way to somewhere else entirely. The solar wind, but that constant stream of charged particles flowing from our sun, caught these sublimated gases and dust and swept them backward, creating the comet's tail, or rather tails, because comets typically have two. There's the dust tail, which follows the comet's orbital path like a cosmic contrail. The dust particles are relatively heavy and move slowly, tracing out the comet's recent path through space. Then there's the ion tail, made of charged gas molecules that always points directly away from the sun, like a windsock in a stellar breeze. These two tails can create spectacular displays. The dust tail often appears yellowish or white, reflecting sunlight like a cosmic cloud. The ion tail glows blue or green from the fluorescence of ionized molecules, particularly carbon compounds. From Earth, depending on our viewing angle, these tails can appear to stretch across significant portions of the sky for bright comets. For 3I/ATLAS, the tails were more modest, visible only through telescopes, but they were there nonetheless, proof that this ancient ice was responding to our sun's warmth. The physics of comet tails is surprisingly complex and beautiful. The dust tail forms because small particles of rock and ice are gently pushed away from the comet by the pressure of sunlight itself. Yes, light has pressure. It's a concept that seems almost magical but is entirely real. Every photon that bounces off a dust particle gives it a tiny push. Multiply that by countless photons and countless particles, and you get a tail that can stretch for millions of miles. The ion tail is even more exotic. The solar wind, traveling at hundreds of miles per second, slams into the gas molecules sublimating from the comet. These collisions strip electrons from the molecules, creating ions. These ions then get caught up in the sun's magnetic field, which extends throughout the solar system, and are channeled into a narrow tail that can extend for tens of millions of miles. It's like a cosmic aurora painted across the darkness of space. When 3I/Attilas was at its brightest, in late 2024 and early 2025, observers around the world turned their telescopes skyward to catch a glimpse of this interstellar visitor. Unlike some comets that become visible to the naked eye, 3I/Attilas remained relatively faint, requiring binoculars or a small telescope to see clearly, but what it lacked in brightness, it made up for in significance. Every photon of light reflecting off this comet had traveled across interstellar space to reach our eyes. Amateur astronomers spent cold winter nights tracking the comet as it moved against the background stars. They set up their telescopes in backyards and dark sky sites, often driving hours to escape light pollution. They attached cameras to their telescopes, taking long exposures to capture the faint glow of the comet. Some stayed up all night, taking image after image, later stacking them together to create portraits of our interstellar visitor that revealed details invisible to the eye alone. Professional astronomers studied 3I/Atlas with every instrument they could point at it. The world's great observatories, Meekick in Hawaii, the Very Large Telescope in Chile, the Hubble Space Telescope in orbit, all took turns observing the comet. Each telescope brought different capabilities to bear. Some could analyze the comet's spectrum in exquisite detail. Others could track its position with incredible precision. Still others could detect the faint heat radiation from the comet's nucleus. They analyzed its spectrum, used the specific wavelengths of light it reflected and emitted to understand its composition. Spectroscopy is one of astronomy's most powerful tools. By spreading light out into its component colors, like a prism creating a rainbow, astronomers can identify specific molecules and atoms. Each element and compound has its own unique spectral fingerprint. It's like being able to determine the ingredients in a cake just by looking at it from across the room. The spectrum of 3I/Attilas revealed a composition both familiar and foreign. They found water ice, as expected. Water is one of the most common molecules in the universe, but they also found more exotic compounds: carbon monoxide, carbon dioxide, methanol, and complex organic molecules. The term organic in chemistry doesn't mean living, but rather molecules containing carbon-hydrogen bonds. These are the building blocks of life as we know it, frozen and preserved in this cosmic time capsule. Some of the most intriguing discoveries came from analyzing the isotope ratios in the comet. Isotopes are versions of elements with different numbers of neutrons. For example, most hydrogen has no neutrons, but deuterium, also called heavy hydrogen, has one. The ratio of deuterium to regular hydrogen can tell us about the conditions where the water formed. 3I/Atlas had isotope ratios slightly different from what we typically see in our solar system, another piece of evidence for its alien origin. The presence of complex organic molecules in 3I/Atlas was particularly exciting for astrobiologists, scientists who study the potential for life elsewhere in the universe. These molecules included things like formaldehyde, methanol, and possibly even amino acids, the building blocks of proteins. While this doesn't mean there's life on the comet, these molecules can form through non-biological processes. It does show that the basic ingredients for life are common throughout the galaxy. This discovery leads us to one of the most profound and sleep-worthy thoughts about interstellar comets like 3I/Atlas. These objects might be one of the ways that the basic ingredients for life spread throughout the galaxy. Imagine stars as cosmic gardens, each growing their own unique chemistry in the stellar nurseries where they're born, in the protoplanetary disks where planets form, in the complex chemistry that occurs on planetary surfaces. When a star dies or when gravitational disruptions occur, some of that chemistry gets scattered into space in the form of comets and asteroids. These then journey between stars, occasionally passing through other solar systems, perhaps even occasionally colliding with planets. This process, called panspermia, when it involves the spread of actual life, or lithopanspermia when it involves the spread of life's building blocks, might be constantly occurring throughout the galaxy. It's entirely possible, minus scientists would say probable, minus the Earth itself has been hit by interstellar comets in its past. The Late Heavy Bombardment, a period about 4 billion years ago when the inner solar system was pelted with comets and asteroids, might have included some interstellar visitors. Some of the water in our oceans, some of the organic molecules that became life, might have originated around other stars and been delivered here by ancient cousins of 3I/Atlas. As you lay there in the quiet darkness, Consider that some of the hydrogen atoms in the water beside your bed might have formed in the Big Bang, been processed through an alien star, frozen into an interstellar comet, and traveled for millions of years before becoming part of Earth and eventually part of you. This isn't just poetic speculation. Scientists have found that some meteorites contain microscopic grains that predate our solar system. These presolar grains formed around other stars and were incorporated into the cloud of gas and dust that eventually became our sun and planets. If solid grains can survive the journey between stars, why not ice and organic molecules protected inside comets? The trajectory of 3I/ATLS through our solar system was carefully mapped by astronomers. It approached from above the plane of the solar system, what astronomers call a retrograde orbit, moving in the opposite direction to most of our local planets and asteroids. This unusual approach angle was another clue to its interstellar origins. Objects that formed in our solar system tend to orbit in the same direction, like cars on a cosmic highway all following the same traffic pattern. But 3I/ATLS was clearly driving on a different road entirely. The plane of our solar system, called the ecliptic, is like a vast disk with the sun at its center. All the planets orbit within a few degrees of this plane, and most asteroids and comets do too. This common orientation is a relic of our solar system's formation, when a rotating disk of gas and dust gradually condensed into the sun and planets. Everything that formed from that disk retained its original direction of rotation. But 3I/ATLS came from outside this orderly system. Its approach from above the ecliptic, at a steep angle, immediately marked it as unusual. As it plunged toward the sun, it crossed the orbits of the outer planets, Neptune, Uranus, Saturn, Jupiter, like a needle threading through rings. Each planet's gravity tugged at it slightly, but none could capture it or significantly alter its course. At its closest approach to the Sun, called perihelion, 3I/ATLS came within about 100 million miles of our star. That might sound far, Maya, and it is, roughly the same distance as Earth from the Sun, but for an object moving as fast as 3I/ATLS, it was just a brief cosmic handshake. The comet's velocity was measured at over 40 miles per second relative to the Sun. At that speed, you could travel around Earth's equator in about 10 minutes. You could reach the moon in less than 2 hours. You could cross the entire United States in about a minute. This tremendous speed is another indicator of 3I/ATLS' interstellar nature. Objects bound to our solar system have maximum speeds determined by their distance from the Sun. It's like rolling a ball up a hill. Miles the higher you start, the faster it will be going when it reaches the bottom. But there's a maximum speed for any given starting height. 3I/ATLS was moving faster than that maximum, like a ball that had been thrown rather than rolled, carrying extra energy from its original stellar system. During its passage through the inner solar system, 3I/ATLS was continuously monitored by both professional and amateur astronomers. Every clear night, telescopes around the world tracked its progress. As Earth rotated, observers handed off their watch like relay runners passing a baton. When the comet set in Europe, observers in America picked up the observation. When it set in America, observers in Asia and Australia continued the vigil. This global collaboration created an almost continuous record of the comet's behavior. Astronomers watched for outbursts and sudden increases in brightness that occur when fresh ice is exposed or when pockets of volatile gases suddenly sublimate. They monitored its rotation, looking for changes that might indicate jets of gas acting like tiny rocket engines. They measured its size, its color, its temperature, building up a comprehensive portrait of this interstellar visitor. As 3I/ATLS swung around the Sun and began heading back out into interstellar space, astronomers continued to observe it for as long as they could. Each observation was precious because we knew we would never see this particular comet again. Unlike the periodic comets that return every few decades or centuries, 3I/ATLS was on a one-way journey. It came from infinity and was returning to infinity. The concept of infinity in space is something our minds struggle to grasp. We're used to boundaries, edges, limits. But space, as far as we know, goes on forever in all directions. 3I/ATLS came from somewhere out in that infinity and will return to it. Its path through our solar system was just an insignificant detour in a journey without beginning or end. There's something deeply poignant about this, isn't there? In our age of instant communication and global connection, where everything feels permanent and recorded, where we can revisit any moment through photographs and videos, 3I/ATLS reminded us that some things truly are once-in-a-lifetime events. or rather once in the lifetime of our entire species. No human who has ever lived has seen this comet before, and no human who will ever live will see it again. Think about that for a moment. Every human who has ever looked at the night sky, from our earliest ancestors in Africa to the astronomers who discovered 3I/ATLAS, has seen a slightly different sky. Stars are born and die. They move through space, slowly changing the patterns of the constellations. Comets come and go, and each generation of humans sees a unique snapshot of an ever-changing cosmos. But the scientific legacy of 3I/ATLAS will endure long after its light has faded from our telescopes. Every interstellar object we detect teaches us something new about the galaxy we inhabit. They're like messages in bottles from other star systems, each one carrying information about conditions in parts of the galaxy we'll likely never visit. The composition of 3I/ATLAS tells us about the chemistry of its parent star system. Its structure tells us about the processes that formed it. Its trajectory tells us about the gravitational influences it encountered on its journey. One of the most intriguing aspects of 3I/ATLAS was its apparent stability. Unlike some comets that fragment or disintegrate when they approach the Sun, 3I/ATLAS held together remarkably well. This suggests it had a relatively solid structure, perhaps with less volatile ice and more rocky material than typical solar system comets. It had survived millions of years in interstellar space and the thermal shock of approaching our Sun might, a testament to its robust construction. The survival of 3I/ATLAS through its solar passage also tells us something about the conditions in interstellar space. The fact that it retained so much ice after such a long journey suggests that interstellar space, while cold and empty, isn't as erosive as we might think. Cosmic rays, high-energy particles that zip through space at nearly the speed of light, constantly bombard objects in space. Over millions of years, this bombardment can erode surfaces and break down molecules. But 3I/ATLAS survived this cosmic sandblasting remarkably intact. Scientists used the observations of 3I/ATLAS to refine their models of how interstellar objects form and travel. Every detail mattered: how quickly it brightened as it approached the Sun, how its tail developed, how its rotation changed. These observations will help us identify and understand future interstellar visitors more quickly and completely. The rotation of 3I/ATLAS was particularly interesting to scientists. Most comets rotate in complex ways, tumbling through space rather than spinning smoothly like a top. This tumbling is often the result of jets of gas pushing unevenly on the comet's surface. By carefully tracking 3I/ATLAS's brightness over time, astronomers could determine its rotation period and whether that rotation was changing. What they found was that 3I/ATLAS was rotating relatively slowly, perhaps once every 10 to 20 hours. This slow rotation suggested that it hadn't been significantly affected by outgassing jets, at least not yet. It was still rotating much as it had during its long journey through interstellar space. This primordial rotation, imparted when the comet first formed or when it was ejected from its home system, had been preserved for millions of years. And there will certainly be future visitors. In fact, with our improving technology and new survey telescopes coming online, we expect to discover interstellar objects much more frequently in the coming years. The Vera Rubin Observatory, set to begin operations soon, will photograph the entire visible sky every few nights. It will likely discover dozens or even hundreds of interstellar objects, turning what once seemed miraculous into almost routine. This new telescope, formerly known as the Large Synoptic Survey Telescope, will be a game-changer for astronomy. With its 3.2 billion pixel camera mitas, the largest digital camera ever built, it will be able to detect objects far fainter than current surveys can see. It will create a movie of the night sky, showing everything that moves or changes. Asteroids, comets, variable stars, supernovae, nothing will escape its unblinking eye. But even as these discoveries become more common, each one will remain special. Each interstellar object is a unique ambassador from another part of our galaxy, carrying secrets we're only beginning to learn how to read. Some might be ancient relics from the galaxy's youth, formed when the first generation of stars were dying and seeding space with heavy elements. Others might be relatively young, ejected from planetary systems that are still forming. Some might be rocky, others icy, and perhaps some will be unlike anything we've seen before. There's been speculation among scientists about whether we might one day be able to send a spacecraft to intercept an interstellar object. The challenge is immense. These objects are discovered with little warning and move incredibly fast. By the time we spot one, It's often already at its closest approach to Earth, and it's moving far too fast for our current spacecraft to catch up. But engineers and mission planners are working on solutions. One idea is to have a spacecraft ready to launch at short notice, sitting on the launch pad waiting for the discovery of a suitable target. Another is to park a spacecraft at one of the Lagrange points MITES locations in space, where the gravitational forces of Earth and the Sun balance out, MITES ready to chase after any interstellar object that passes nearby. The European Space Agency has proposed a mission called Comet Interceptor that would wait in space for an interesting target, whether a long-period comet from our own Oort cloud or an interstellar visitor. When a suitable target is identified, the spacecraft would spring into action, racing to intercept the object and study it up close. Imagine being able to sample material from another star system, to analyze chemistry that formed under alien suns. It would be like reaching across the vast loneliness of space to shake hands with another world. Some scientists have even more ambitious dreams. They imagine not just intercepting an interstellar object, but landing on one, hitchhiking on it as it journeys through space. Such a mission would be a one-way trip to the stars, taking thousands or millions of years to reach another star system. It's the stuff of science fiction now, but so was detecting interstellar objects just a decade ago. For now, though, we must be content with observation from afar, and there's something beautiful in that limitation. It reminds us that the universe is vast beyond imagination, that there are wonders we can glimpse but not grasp, mysteries we can acknowledge but not fully solve. As you drift towards sleep, there's comfort in knowing that the cosmos continues its ancient dance whether we're watching or not. The departure of 3I/ATLAs from our solar system wasn't dramatic. There was no fanfare, no cosmic send-off. It simply grew fainter and fainter in our telescopes, until even our most sensitive instruments could no longer detect it. The last confirmed observation was made in early 2025, when the comet was already beyond the orbit of Mars and heading rapidly outward. But it continues on its journey even now. As you listen to these words, it's already millions of miles past where we last saw it, heading back into the profound darkness between stars. As it climbs away from the sun, it's cooling down again. The jets of gas that briefly brought it to life are shutting down. The coma that surrounded it like a glowing cloud is dissipating. Soon it will return to the frozen, dormant state in which it spent millions of years a sleeping traveler in the night. Where will it go next? The truth is, we don't really know. Space is so vast and stars are so relatively sparse that 3I/ATLAs might travel for millions more years before encountering another star system. The nearest stars to our sun are over 4 light-years away, and 3I/ATLAs isn't heading directly toward any of them. It might wander through the galaxy for longer than our sun has left to live, a permanent nomad in the cosmic dark. When it does eventually encounter another star system, if that system harbors intelligent observers, they might look up and wonder about this visitor just as we did. They might analyze its spectrum and find traces of its passage through our solar system, molecules it picked up during its brief warming by our sun, isotopes that are characteristic of our local chemistry. They might wonder about the star system it visited, perhaps developing theories about what kind of star could have altered the comet in the ways they observe. In this way, 3I/ATLAs is carrying a little bit of our solar system with it on its continued journey. Some of the atoms in its tail, blown off during its passage around our sun, are now part of interstellar space, and some of the atoms it shed while passing through our solar system are now part of our local environment. They're drifting through space, perhaps to be swept up by our sun's solar wind and carried to the outer reaches of our solar system, perhaps to fall toward the sun and eventually be incorporated into the solar wind itself, perhaps eventually to rain down on planets and become part of their atmospheres or surfaces. This exchange of material between star systems is happening all the time, a slow cosmic metabolism that connects all parts of our galaxy. We tend to think of star systems as isolated islands in space, but interstellar objects like 3I/ATLAs remind us that we're all part of a larger galactic ecosystem. Matter and energy flow between stars over timescales so vast that human history is less than a blink in comparison. Consider the journey of a single water molecule that might have been part of 3I/ATLAs. It formed billions of years ago, perhaps in the cooling envelope of a dying star. The oxygen atom in it was forged in the star's core through nuclear fusion, while the hydrogen atoms date back to the Big Bang itself. This molecule was incorporated into a growing comet in a protoplanetary disk around a young star. For billions of years it remained frozen in that comet as it orbited its star. Then, some cosmic catastrophe, a close encounter with a planet, the death of its star, a collision with another comet, sent it on an interstellar journey. For millions of years, this water molecule tumbled through space as part of 3I/ATLS. Then, as the comet approached our Sun, the molecule sublimated, becoming part of the comet's coma. Perhaps it was blown away by the solar wind and is now drifting through our solar system. Perhaps it will eventually find its way to Earth, joining our oceans or atmosphere. Perhaps billions of years from now, it will be part of a living organism, helping to carry genetic information or regulate cellular processes. This is the kind of deep-time, deep space story that 3I/ATLAS represents. It's a story that makes our daily concerns seem both insignificant and precious. Insignificant because we're such a small part of such a vast universe. Precious because we're the only part of the universe, as far as we know, that can appreciate and understand these cosmic connections. As we learn from studying 3I/ATLS, these interstellar visitors might be far more common than we ever imagined. Some scientists now believe that our own solar system might have captured some interstellar objects in the distant past. There could be comets in the outer reaches of our solar system that originally formed around other stars, cosmic immigrants that have been here so long we think of them as natives. The Oort cloud, that vast sphere of comets that surrounds our solar system at a distance of nearly a light-year, might contain some of these captured interstellar objects. When we see a long-period comet falling toward the Sun from the Oort cloud, we assume it formed in our solar system and was kicked out to its distant orbit by gravitational interactions with the giant planets. But what if some of these comets are actually interstellar visitors that were captured billions of years ago? This raises fascinating questions about identity and belonging on a cosmic scale. If a comet formed around another star but has been orbiting our Sun for billions of years, is it still an interstellar object? If Earth's oceans contain water delivered by interstellar comets, are we partly extraterrestrial? These aren't questions with easy answers, but they're wonderful to contemplate as your mind relaxes and wanders. The study of 3I/ATLAS also reminded us how much we still don't know about our own cosmic neighborhood. We've discovered over 1 million asteroids and thousands of comets in our solar system, but we've barely scratched the surface. The outer solar system, beyond Neptune, remains largely unexplored. There could be countless objects out there, some perhaps captured interstellar visitors like ancient versions of 3I/ATLAS, waiting to be discovered. The Kuiper Belt, that region of icy bodies beyond Neptune where Pluto resides, is thought to contain hundreds of thousands of objects larger than 60 miles across, and trillions of smaller ones. We've only directly observed a tiny fraction of these. Each one is a frozen time capsule from our solar system's formation, and possibly some are visitors from other stars. Beyond the Kuiper Belt lies the scattered disk, a region of objects on highly elliptical orbits that take them far from the Sun, and beyond that, the Oort cloud, so distant that no telescope has ever directly observed an object there. We only know it exists because long-period comets must come from somewhere, and their orbits point back to this distant reservoir. Every year, our ability to detect and study these objects improves. New telescopes with advanced sensors can spot fainter objects and track them more precisely. Computer algorithms can sift through vast amounts of data to find the telltale signs of moving objects against the stellar background. Machine learning systems are being trained to recognize the subtle differences between ordinary solar system objects and interstellar visitors. What once required years of patient observation can now be accomplished in days or hours. A century ago, discovering a comet required hours of painstaking visual observation through a telescope, memorizing star fields and looking for anything that had moved. Today, automated surveys can discover dozens of comets per year, and computers can calculate their orbits within hours of discovery. But technology isn't the only thing advancing. Our understanding of the physics and chemistry of comets continues to deepen. We've sent spacecraft to several comets, even landing on one Minos, the European Space Agency's Rosetta mission to Comet 67P/Churyumov-Gerasimenko. These missions have revealed comets to be far more complex and interesting than we ever imagined. We've learned that comets aren't just dirty snowballs, but complex worlds in their own right. They have cliffs and valleys, boulders and plains. They have layers that record their history like tree rings. They have caves and pits that might preserve primordial ices from the solar system's birth. They have organic molecules so complex that some scientists wonder if comets might have delivered the precursors to life on Earth. 3I/ATLAS contributed to this understanding in unique ways. Because it came from outside our solar system, it served as a natural experiment, a control group against which we could compare our local comets. The similarities told us about universal processes that occur throughout the galaxy. The differences told us about the unique conditions in different star systems. One of the most striking findings was how normal 3I/ATLS appeared to be, at least in terms of its composition. It wasn't made of exotic materials or strange isotopes. It was water, ice, rock, dust, and organic molecules, the same ingredients we find in our own comets. This suggests that the basic chemistry of planetary formation might be similar throughout our galaxy, which has profound implications for the possibility of life elsewhere. If the building blocks are the same everywhere, if water and organic molecules are common throughout the galaxy, then the conditions for life might be common too. This doesn't mean life itself is common minds. That's still an open question, but at least the raw materials are widely available. Every star system might be running its own experiment in chemistry and biology, and interstellar comets might occasionally cross-contaminate these experiments. As you settle deeper into rest, consider the chain of coincidences that allowed us to observe 3I/ATLS at all. It had to pass close enough to Earth to be detected, but not so close as to be dangerous. It had to arrive at a time when we had the technology to spot it and understand what it was. It had to be large enough and reflective enough to see with our current instruments. It had to survive its passage around the Sun without fragmenting. The odds of all these factors aligning are astronomically small, which makes our brief encounter all the more precious. Yet this also tells us something hopeful. If we could detect 3I/ATLS despite all these challenges, imagine how many more wonders await discovery. Every night, astronomers around the world point their telescopes at the sky, searching for the next surprise, the next visitor, the next piece of the cosmic puzzle. Sometimes they find something extraordinary like 3I/ATLS. More often, they add small but important observations to our ever-growing understanding of the universe. There's a quiet heroism in this work, isn't there? Night after night, often in remote locations, astronomers carry out their observations. They deal with clouds and equipment failures and budget constraints. They spend years analyzing data that might yield no dramatic discoveries, but they persist because they know that understanding our universe is a collective endeavor, built one observation at a time. The amateur astronomers who observed 3I/ATLS exemplify this spirit. They didn't have access to giant telescopes or government funding. They had passion, patience, and whatever equipment they could afford or build themselves. Some spent thousands of dollars on telescopes and cameras. Others made do with more modest equipment, pushing it to its limits to glimpse this interstellar visitor. They stood outside on cold winter nights, their breath-forming clouds in the frigid air, carefully tracking the comet as Earth's rotation carried it across the sky. They dealt with dew forming on their lenses, neighbors' lights ruining their dark adaptation, and the constant battle against light pollution. But when they finally captured an image of 3I/ATLS, a faint smudge of light against the stars, all the difficulties were worth it. Some of these observers shared their images online, contributing to a global mosaic of observations. Others kept detailed logs, noting the comet's brightness and position, data that professional astronomers could use to refine their orbital calculations. It was a beautiful example of citizen science, ordinary people contributing to our understanding of an extraordinary event. The story of 3I/ATLAS is also a story of international cooperation. Astronomers from dozens of countries collaborated to observe and study this comet. Data was shared freely across borders and time zones. Russian astronomers shared their observations with American colleagues. Chinese telescopes provided data that European scientists analyzed. Japanese researchers contributed spectroscopic observations that Australian astronomers used to determine the comet's composition. When one part of Earth rotated away from the comet, observers on the other side picked up the watch. As the comet set below the horizon in Hawaii, telescopes in Chile were already tracking it. As it disappeared from view in Australia, observers in South Africa were preparing their equipment. It was a planet-wide effort, humanity working together to understand something larger than ourselves. This cooperation extends beyond just the observations. The software used to calculate 3I/ATLAS's orbit was developed by programmers from multiple countries. The databases that stored the observations are maintained by international consortiums. The scientific papers analyzing the comet's properties have authors from institutions around the world. Science at its best transcends borders and politics, uniting us in our shared curiosity about the universe. As 3I/ATLAS continues its journey into the darkness, it carries with it the accumulated observations and wonder of thousands of humans who took the time to look up and pay attention. In a sense, we've become part of its story, just as it has become part of ours. For a brief moment, our paths crossed in the vastness of space, and we both continued on, slightly changed by the encounter. We've changed because we now know more about interstellar objects, about the galaxy we inhabit, about our place in the cosmic ecosystem. 3I/Atlas has changed too, having lost some of its mass to sublimation, having had its surface altered by solar radiation, carrying traces of its encounter with our sun as it returns to the deep freeze of interstellar space. The next time you see a comet, whether in a photograph or through a telescope or perhaps even with your own eyes, remember 3I/Atlas. Remember that some comets are visitors from unimaginably far away, carrying messages from other stars. Remember that we live in a galaxy where matter and energy flow between star systems in a slow, eternal dance. Remember that we're all made of star stuff, some of which might have traveled here from very far away indeed. The legacy of 3I/Atlas extends beyond just the scientific data it provided. It captured public imagination in a way that few astronomical events do. News outlets around the world covered its discovery and passage. Social media buzzed with discussions about what it meant to observe an object from another star system. Parents pointed it out to their children through telescopes, planting seeds of wonder that might grow into lifelong interests in science. In schools, teachers used 3I/Atlas as a teaching tool, explaining orbits and gravity, the formation of solar systems, the scale of interstellar distances. Students calculated its speed and trajectory, learning physics through a real-world example. Some were inspired to pursue careers in astronomy or space science, their paths altered by this brief celestial visitor. Museums and planetariums created special shows about 3I/Atlas, using sophisticated visualizations to show its journey through space. Visitors could see the comet's path from multiple perspectives, from Earth, from the Sun, from outside the solar system entirely. They could watch its tail develop as it approached the Sun, see the jets of gas erupting from its surface, follow its trajectory back to the depths of interstellar space. Artists were inspired by 3I/Atlas too. Paintings and sculptures attempted to capture the lonely beauty of its journey. Musicians composed pieces inspired by the idea of an eternal traveler, crossing the void between stars. Poets wrote about time and distance, about meetings and partings, about the connections that bind the universe together. This cosmic visitor became a muse, inspiring creativity across cultures and continents. Science fiction writers imagined stories about 3I/Atlas. What if it wasn't natural, but an ancient alien probe? What if we could land on it and ride it to another star? What if it was carrying microscopic life, dormant for millions of years but ready to wake in the warmth of a sun? While these stories were fiction, they helped people engage with the real science, thinking about possibilities and implications. But for now, as you drift closer to sleep, let's return to the present moment. Right now, 3I/Atlas is somewhere out there, tumbling through the darkness, returning to the profound cold and silence of interstellar space. It's moving away from us at tremendous speed, already far beyond the orbit of Neptune, heading for the heliopause where the solar wind finally gives way to the interstellar medium. The heliopause is a fascinating boundary, the edge of our sun's sphere of influence. Inside it, the solar wind dominates, creating a bubble in interstellar space called the heliosphere. Outside it, the interstellar medium takes over, with its own magnetic fields and particle winds from distant stars. Only 2 human spacecraft have crossed this boundary, Voyager 1 and Voyager 2, and they're still sending back data about conditions in interstellar space. 3I/Atlas will cross this boundary much faster than the Voyagers, which took decades to reach interstellar space. Within a few years, our interstellar visitor will truly return to the realm between stars. The sun's gravity will continue to tug at it, ever so slightly, but it will never be enough to bring it back. The comet will feel our sun's gravitational influence for thousands of years, an invisible thread connecting it to our star even as it journeys deeper into the galaxy. As it travels, 3I/Atlas will slowly return to its dormant state. The last wisps of its coma will dissipate into space. The dust grains that formed its tail will either fall back onto its surface or drift away forever. Its surface, briefly activated by the sun's heat, will freeze solid again. It will become once more what it was for millions of years, a Nyx, a silent, frozen traveler in the darkness. But it won't be exactly the same as it was before. Its passage through our solar system has left its mark. Some of its more volatile ices are gone, sublimated away during its solar approach. Its surface has been altered by solar radiation and the thermal stress of heating and cooling. It might be rotating slightly differently due to the jets of gas that erupted from its surface. It carries the scars of its brief encounter with our Sun. In 1 billion years, if 3I/Etelaz encounters another star system with intelligent observers, they might be able to detect these changes. They might wonder what star the comet previously visited, what kind of radiation it was exposed to, what caused the patterns of erosion on its surface. They might even be able to determine that it passed through a G-type star system like ours based on the specific ways it was altered. This is how the galaxy slowly shares information about itself, through these traveling messengers that carry physical and chemical records from star to star. It's an incredibly slow form of communication, taking millions of years for each message to be delivered. It's real and ongoing. The galaxy is talking to itself through objects like 3I/Etelaz, and we've just learned how to listen to these messages, and what stories it could tell. If comets could speak, 3I/Etelaz would have tales of its birth in a stellar nursery, possibly billions of years ago when the galaxy was younger and more turbulent. It might describe the protoplanetary disk where it formed, swirling with gas and dust, lit by a young star still settling into its main sequence life. It might tell of sister comets and brother asteroids, formed from the same cloud but scattered to different fates. It would tell of the event that ejected it from its home system. Was it a close encounter with a giant planet, its gravity acting like a slingshot? Was it the death throes of its parent star, expanding into a red giant or exploding as a supernova? Was it a collision with another comet, both objects shattered with some pieces falling inward and others flung outward? We'll never know for certain, but each possibility tells a different story about the dynamics of planetary systems. Then would come the long, quiet chapters of its interstellar journey. Millions of years of silence and darkness, tumbling through the void with no company but distant starlight. Occasionally, perhaps once in 1 million years, passing close enough to a star to feel its warmth but never close enough to be captured. A cosmic wanderer neither here nor there, belonging to no star but influenced by all of them through their combined gravity. It might describe the gradual changes in the stellar neighborhood as it traveled. Stars being born in distant nebulae, their first light reaching the comet after thousands of years of travel. Other stars dying, their light suddenly extinguished from the comet's perspective. The slow dance of stellar motion, with stars that were once ahead falling behind, and new stars appearing on the horizon of its journey. And finally, it would tell of its encounter with our Sun, that brief warm chapter in its long cold story. The gradual awakening as solar radiation reached its surface, the strange sensation of sublimation after millions of years of being solid ice, the development of its coma and tail, like a butterfly briefly emerging from a chrysalis only to return to it again, the gravitational tugs of our planets, each one leaving a tiny mark on its trajectory. But comets don't need to speak. They tell their stories in the language of light and motion, chemistry and physics, and we're learning to read that language. Slowly but surely, one observation at a time, one discovery at a time, one wonder at a time. As your eyes grow heavy and your breathing deepens, take a moment to appreciate the extraordinary privilege of living in a time when we can detect and study objects like 3I/Etelaz. For all of human history, until very recently, such objects passed by unnoticed and unknown. Our ancestors might have seen bright comets in the night sky, but they had no way of knowing that some of them came from other stars. Think about all the interstellar objects that must have passed through our solar system over the billions of years of its existence. During the age of the dinosaurs, when giant reptiles ruled the Earth, interstellar comets sailed silently overhead, unseen and unappreciated. During the rise of mammals, as our distant ancestors developed larger brains and began using tools, these cosmic visitors continued their passages, leaving no record except perhaps a few more water molecules in our oceans. Even during recorded human history, how many interstellar objects passed by without our knowledge? When the pyramids were being built in Egypt, when Rome ruled the Mediterranean, when Columbus sailed to the Americas, when Newton was formulating his laws of motion, all these times, interstellar visitors were likely passing through our solar system, invisible to the observers of those eras. But now we have eyes that can see across billions of miles, minds that can comprehend billions of years, and hearts that can appreciate the profound beauty of a dirty snowball tumbling through space. We live in the first era of human history, when we can detect these cosmic messengers, read their chemical signatures, calculate their origins and destinations. It's a remarkable time to be alive and aware. There's something deeply comforting about the journey of 3I/Atlas, isn't there? It reminds us that the universe is vast but not empty, ancient but not static, foreign but not entirely alien. It reminds us that we're part of something immense and ongoing, a cosmic story that began long before us and will continue long after us. We're not separate from the universe. We're expressions of it, temporary arrangements of atoms that have been cycling through stars and space for billions of years. Some of those atoms are in you right now, as you listen to these words. The calcium in your bones was forged in the heart of a dying star. The iron in your blood was created in a supernova explosion. The hydrogen in the water that makes up most of your body was formed in the first moments after the Big Bang. You are, quite literally, made of cosmic material. You are the universe contemplating itself, if only for a brief moment. And someday, billions of years from now, some of your atoms might find themselves in an interstellar comet, carrying the essence of Earth to distant stars. They might sail through the galaxy for millions of years, visiting star systems we can only dream of, before finally being incorporated into a new planet, perhaps even becoming part of new life. The atoms that allow you to think and dream tonight might one day allow other beings to think and dream under alien suns. But that's a story for another time, another night, another gentle journey into wonder. For now, it's enough to know that 3I/Atlas came and went, a cosmic visitor that reminded us of our place in the grand scheme of things. It showed us that we're not alone in the universe, not in the sense of intelligent life necessarily, but in the sense that material and energy connect all things across space and time. The universe is a vast web of connections, with gravity and light, chemistry and physics binding everything together. Stars form from gas clouds that contain atoms from previous generations of stars. Planets form from the debris around young stars, incorporating materials that have been processed through multiple stellar generations. Life, if it exists elsewhere, is built from the same elements that build life here, arranged perhaps in different ways but following the same fundamental laws of chemistry. And threading through this web are the wanderers like 3I/Atlas, carrying materials and information from one star system to another. They're like the universe's circulatory system, slowly but steadily moving materials around the galaxy. They ensure that no star system is truly isolated, that all are part of the greater galactic community. As you continue to settle into rest, perhaps approaching that gentle boundary between waking and sleep, remember that boundaries are often more fluid than they appear. The boundary between our solar system and interstellar space, between one star system and another, between the cosmic and the personal mindness, these are all softer and more permeable than we might think. 3I/Atlas crossed these boundaries, and in observing it, so did we. When we looked at 3I/Atlas, we weren't just seeing a comet, we were seeing billions of years of cosmic history condensed into a single object. We were seeing the death of an ancient star, the birth of a planetary system, the complex chemistry that might lead to life, the vast distances and times that separate stars, and the connections that nevertheless bind them together. We were seeing our own cosmic heritage and future, written in ice and rock and organic molecules. Tonight, as you sleep, 3I/Atlas continues its eternal journey through the darkness. It's out there right now, this very second, tumbling slowly through space, carrying its ancient secrets further and further from our small blue world. By the time you wake tomorrow, it will be millions of miles farther away. By next week, it will have traveled a distance greater than that between Earth and Mars. By next year, it will be beyond the reach of our most powerful telescopes. We'll never see it again, but we'll remember it. We'll remember what it taught us about the galaxy we inhabit, about the connections between stars, about our own cosmic heritage, and more importantly, we'll remember how it made us feel, small but significant, isolated but connected, temporary but part of something eternal. The data collected from 3I/Atlas will be analyzed for years to come. Graduate students will write dissertations about its composition. Theorists will use it to test models of planetary system formation and evolution. Engineers will use lessons learned from tracking it to design better systems for detecting future interstellar objects. Teachers will use it as an example when explaining orbital mechanics and spectroscopy to future generations of students. And perhaps most importantly, 3I/Atlas has prepared us for future interstellar visitors. We now know what to look for, how to quickly determine if an object is interstellar, what observations are most important to make while we have the chance. The next interstellar object we detect, 9ast, and there will be a next one perhaps soon, will be studied even more thoroughly because of what we learned from 3I/ATLAS. Perhaps that's the most beautiful thing about 3I/ATLAS. Not that it came from so far away, not that it was so ancient, not even that we were able to detect and study it. The most beautiful thing is that it reminded us to look up, to wonder, to ask questions about our place in the universe. It reminded us that every night, the sky is full of mysteries waiting to be discovered, stories waiting to be told, wonders waiting to be appreciated. In our modern world, with its artificial lights and digital distractions, it's easy to forget that we live on a planet orbiting a star in a galaxy full of other stars. It's easy to lose sight of the cosmic perspective, to become so focused on our daily concerns that we forget we're part of something much larger. But objects like 3I/ATLAS remind us of the bigger picture. They reconnect us with the cosmos, even if just for a moment. So as you drift off to sleep, perhaps you'll dream of cosmic snowballs sailing through the darkness, of ancient chemistry preserved in ice, of connections that span light years and eons. Perhaps you'll dream of being an astronomer, discovering the next interstellar visitor, adding your own chapter to humanity's growing understanding of the universe. Or perhaps you'll dream of being a comet yourself, free to wander wherever gravity and momentum take you, carrying messages between stars, witnessing the slow evolution of the galaxy over millions of years. Whatever dreams come, know that you're part of this cosmic story. The atoms in your body, the thoughts in your mind, the dreams in your sleep, they're all part of the same universe that created 3I/ATLAS and brought it briefly into our lives. We are the universe understanding itself, one comet, one observation, one wonder at a time. As sleep approaches, let your mind wander among the stars. Imagine the galaxy as it really is, not the static picture we see from Earth, but a dynamic, evolving system with stars being born and dying, planets forming and being destroyed, comets wandering between stellar systems. Imagine the countless interstellar objects out there right now, each one carrying secrets from distant stars, each one a messenger in the galaxy's slow conversation with itself. And remember that you're not just an observer of this cosmic dance, you're a participant. The gravity of your body, infinitesimally small though it is, influences everything in the universe. The light from your phone or bedside lamp is spreading out into space at 186,000 miles per second, carrying information about Earth to any alien astronomers who might detect it. The heat from your body is radiating infrared photons that will travel forever through space unless absorbed by something else. You are connected to everything meaningless, to 3I/ATLAS continuing its journey through the darkness, to the stars shining overhead, whether you can see them or not, to the galaxies billions of light years away, to the quantum fluctuations in the vacuum of space. These connections might be subtle, might be impossible to measure with our current technology, but they're real. The universe is one interconnected whole, and you're an integral part of it. Thank you for joining me on this journey through space and time, exploring the remarkable story of Comet 3I/ATLAS. Thank you for your curiosity, your attention, and your willingness to contemplate the cosmos with me. Thank you for being part of this global community of wonder seekers, people who find comfort and meaning in understanding our place in the universe. If you enjoyed this gentle voyage into astronomical wonder, please consider subscribing so you never miss these peaceful explorations of science. Leave a comment if you're still awake. I'd love to know where in the world you're listening from. Are you in a city where light pollution hides the stars, but where human creativity shines bright? Are you somewhere rural where the Milky Way stretches across the sky in all its glory? Are you perhaps in the southern hemisphere where different stars wheel overhead, where the Southern Cross points the way? Wherever you are, whatever time it is for you, I hope you found some peace in contemplating this cosmic visitor. I hope the story of 3I/ATLAS has given you something to ponder as you drift toward dreams, some perspective on the beautiful complexity of the universe we inhabit. I hope it's reminded you that you're part of something ancient and ongoing, something vast and beautiful, something that connects all things across space and time. Sleep well, dream of distant comets and ancient ice, and remember, you are made of star stuff, connected to everything in the cosmos, including lonely comets sailing through the darkness. The universe is vast and sometimes cold, but it's also beautiful and interconnected and constantly in motion, and you're part of it all. In the morning when you wake, the world might seem ordinary again, but remember that Earth itself is a kind of spaceship carrying us all through the cosmos at tremendous speeds. We're orbiting the Sun at 67,000 miles per hour. Our solar system is orbiting the center of the galaxy at 450,000 miles per hour. Our galaxy is moving through space at over 1,000,000 miles per hour. We're all cosmic travelers, just like 3I/8LS, following our own paths through the universe. The difference is that we can appreciate the journey. We can look up and wonder. We can study objects like 3I/8LS and learn about our place in the cosmos. We can share that knowledge with others, passing on the wonder to future generations. We can be the universe's way of understanding and appreciating itself. Good night, sweet dreams, and may your sleep be as peaceful as the silent journey of 3I/Atlas through the stars. May you rest as deeply as space is vast, and may you wake refreshed and ready to appreciate the wonders that surround us, from the cosmic to the commonplace, from interstellar visitors to the morning light that will greet you when you wake. The universe continues its dance while you sleep. Stars are born and die, comets sail through the darkness, planets spin on their axes, and the great cosmic story continues. But for now, for you, there is only rest, only peace, only the gentle embrace of sleep. Let go of the day's concerns. Let your mind float free among the stars. Let sleep carry you away like a comet on an endless journey through the peaceful darkness. Until next time, this has been Sleep About Science, reminding you that wonder and rest can exist in the same quiet moment, that learning and letting go can happen simultaneously, and that sometimes the most profound thoughts come when we're drifting off to sleep, contemplating comets sailing through the eternal night. Sweet dreams, cosmic travelers. Good night.